Hi, everyone. Welcome to the inaugural session of our AmeriFlux Luminaries webinar series. This year, as part of our theme on remote sensing activities, we are privileged to host a series of talks by some of the leading figures in the field. And today, we are honored to have Dr. Bill Kustas with us. Dr. Bill Kustas is a research hydrologist and distinguished senior research scientist at the USDS Agricultural Research Service based in Hydrology and Remote Sensing Laboratory in Beltsville, Maryland. With a storied career that began in 1986, Dr. Kustas has dedicated decades to advancing our understanding of how energy exchanges between the land surface and the atmosphere impact our environment, specializing in evapotranspiration processes across scales from local fields to global landscapes. His current projects, including Graybags and T-Rex, focus on refining remote sensing tools to enhance irrigation scheduling and water management in perennial crops, vital for improving agricultural sustainability in regions like California Central Valley. So today, Dr. Kustas will share insights on quantifying surface energy balance and evapotranspiration from field to global scales using remotely sensed land surface temperature. We look forward to a thought-provoking presentation and a vibrant discussion afterward. So please join me in warmly welcoming Dr. Bill Kustas. And Bill, if you're ready, please take it away.
Okay, thank you, Kong. Thank you for having me today. What I'll be describing is a little bit of history of the use of land surface temperature. What you see here are some of the key supporters, researchers who helped develop some of the current applications of the use of land surface temperature and its utility in modeling surface energy balance and evapotranspiration. And you'll see throughout this talk their contributions as part of this work. So, as many of you probably know already, quantifying evapotranspiration and surface energy balance is quite important in understanding the global water and energy cycle. And evapotranspiration in particular is important because it amounts to accounting for a significant portion of precipitation that returns to the atmosphere. It consumes, over 50% of the energy in that radiation. And for agriculture, it's essential in production, obviously. And its use in irrigation is seen as a real significant impact on water resources. As you can see there in that graph, globally, 70% of the fresh water is used for agricultural production. And, there's some large groundwater reservoirs that are being depleted due to mainly agricultural activity as well as effects of climate change. So, early approaches in quantifying evapotranspiration came from the works of, the well-known, Penman-Monteith equation, where Penman's equation was adjusted for the fact that the plants themselves help regulate the amount of water loss. And so incorporating this to model resistance as part of the formulations for estimating evaporation due to both the available energy and the atmospheric demand was incorporated by Penman. And there's been many applications of that approach. There's also been sort of this adjustment for Boucher's hypothesis between potential and actual evaporation that have also been used to try to quantify this at large scale. Some of the work of Wilfred Broussard has gone and developed this technique and has been applied successfully in different landscapes. So, from that type of work, of course, there's been further developments using more sophisticated or complex soil vegetation atmosphere transfer models where now you incorporate the its response to the atmosphere, as well as its phenology and its makeup that causes it to lose water. And so some of the early development by Peter Sellers et al. On developing this simple biosphere model is still being implemented today in many land surface modeling schemes. John Norman has also worked on this approach. And there's real value in understanding how the plants obviously are responding to atmospheric forcing and soil moisture conditions. And a lot's been learned from these modeling approaches and understanding the soil plant atmosphere interactions. The problem is that in applying these type of models over a landscape, there are a number of significant inputs that are unknown and are challenging to obtain when we're looking at more than a small area or field site in applying these models. There's a number of inputs in the soil, as well as inputs from the atmosphere, that are difficult to quantify or have more uncertainty. The idea of using remote sensing, in particular land surface temperature, is the idea that perhaps by knowing the radiative energy inputs, the amount of water loss required to keep those soil and vegetation temperatures by using land surface temperature observations could be a metric or a surrogate to understanding the state of that vegetation land surface condition. Here's an example of how thermal could be very useful, particularly in irrigation conditions. You can see here, the difference between a thermal or non-thermal remote sensing approach. Where irrigation occurs, non-thermal approaches mainly are affected by the amount of vegetation. So irrigation in stages where the vegetation is low cover, or that it's actually bare soil, you won't see that in these type of approaches, whereas in thermal, these can be picked up quite readily by the land surface temperature observations. Another aspect that's been studied over the years, Christopher Heen from NASA has been working together with our group, and in particular Martha Anderson and Wade Crow, who are both from the Hydrology and Remote Sensing Lab, using the Alexi land surface temperature model and comparing it to NOAA water balance models. And what they're seeing is that with these types of land surface water balance model approaches, irrigation and depth to water table are not easily captured by the water balance model. In both cases, it's the land surface temperature that's capturing this water effect, this effect of additional water. Depth to water table, areas where there are phreatophytes that have access to shallow groundwater, are examples of where the land surface temperature information gives you added information that these types of models aren't able to easily utilize. So how did some of these remote sensing models start out using thermal remote sensing? Some of the earliest work on this, besides looking at it from point-based observations, came from John Price and also Toby Carlson, where there was a realization that a vegetation index or fractional cover estimate from vegetation index relation to surface temperature could define sort of boundaries of where there was bare soil versus where there was full vegetated cover. And the temperature response was related to the condition of that surface. So in other words, down there on the right, where you see this, what's called the warm edge, this could be defined as sort of the temperature in which the vegetation has some moisture stress condition versus when there is low temperature conditions up here, and low temperature and high NDVI, or high amount of cover, whereas down in here you have high temperatures but low cover, so this could be a bit dry, bare soil region. This would help define in a model, in this case a land surface model that was run to depict over here moisture condition lines. So anywhere from moisture near zero up to high moisture content conditions. And these could help to define sort of the boundaries of the modeling of moisture and of eventually of evapotranspiration. This contextual-based approach was also being leveraged by models such as Siebel and Metric. Some of you may be familiar with these types of models. In these particular cases, they use the temperature, surface temperature, NDVI or cover approach, as well as albedo estimates to define simple single source energy balance models of defining sort of the wet or cool temperature and the dry, hot temperature to define the limits of the surface energy balance. And I'll describe that a little more in my talk in a little bit here. Now, was going on. Some of you who may be familiar with the Fife first Iselskip field experiment, which occurred in Manhattan, Kansas, the Konza Prairie. This was one of the first large-scale experiments in the U.S. that involved an international group of interdisciplinary research and scientists who were trying to evaluate land surface atmosphere interactions and how satellites might be utilized to help to quantify and monitor surface fluxes, including carbon as well as energy fluxes. Now, in that special issue was sort of an overall synopsis of the findings from the Fife experiment. And in this particular overview article, there was particular mention of surface-based methods for estimating ET, land surface temperature-based methods. And their analysis pointed to the fact that, number one, there was a difference between radiometric and aerodynamic temperatures, where the aerodynamic temperature is the temperature at which the surface air temperature gradient would match the sensible heat flux from that surface, which didn't always match with what the radiometric temperature was. And then utilizing that radiometric temperature in a simple aerodynamic approach caused a lot of scatter. So one of their conclusions was that, as you can see there in that pink box, that that remote estimation of surface temperature to useful accuracies is problematic, and that therefore the use of thermal infrared measurements to infer sensible heat flux is probably not feasible to acceptable accuracies. So this put a damper on the potential use of land surface temperature, cast some doubt on its utility. That actually resulted in this thermal remote sensing workshop that happened in France and was led by Toby Carlson, with the idea of trying to understand what was causing the limitations of using land surface temperature and thermal remote sensing, and what could be ways of changing the direction of the research to make it more useful application for surface energy balance and evapotranspiration monitoring and research. One of the main issues that came out of that meeting was this whole idea of the aerodynamic versus radiometric temperature, and the application of this, as you see the equation down there at the bottom, the radiometric air temperature difference and this resistance term that sort of incorporates many of the complexities that go on with having an observation of radiometric temperature. This has been called the KB-1 a factor or momentum transport versus heat transport is different. It's less efficient in heat transport, and this was a factor that was causing the traditional way of using radiometric temperature and aerodynamic resistance was causing some issues. So, so there was a discussion and debate about what to do about that. John Norman, who at that time was at the University of Wisconsin, proposed a two-source approach to address this issue, being that we needed to explicitly account for the fact that the radiometric temperature was seeing both the soil substrate background and the canopy, and that those two transport mechanisms or the conductance from these two surfaces is very different, and that accounting for this difference and incorporating a way of separating the soil and canopy temperatures would amount to a way to account for this issue with radiometric versus aerodynamic temperature. And so based on, this is actually handwritten notes from that meeting. You could see there September 22nd, 1993. That is, myself and John worked on developing this concept and incorporating it into a modeling system for estimating surface energy balance and evapotranspiration. The basic modeling system is shown there on the right, where you have the total net radiation as a sum of sensible latent heat and soil heat flux. These are partitioned between the soil and canopy surfaces. How that's distributed is a function of the approximation that radiometric temperature is going to be the sum of the canopy and soil substrate temperatures estimated by the fractional amount of canopy and soil being viewed by that sensor. So in fact, this modeling approach treats the soil and plant atmosphere coupling differently. It accommodated, we use a simple formulation to accommodate view angle effects. And in addition to that, by separating or explicitly treating the soil and canopy elements, it actually then partitions those fluxes. The key, besides having this formulation for the sensible heat flux, to solve the set of equations, we needed a transpiration formulation. And the original formulation was based on the idea that the canopy, if it was unstressed, would be evaporating at the Priestley-Taylor value. This is an approximation, obviously, but one that we felt we could first test as a means of estimating the transpiration, and that would then form a set of equations that could be solved. Since the original 1995 paper, there have been other approaches of the transpiration using Penman-Monteith, the light use efficiency approach as well. But the point was that we needed this transpiration formulation for the canopy to solve the solution of equations. And then the latent heat flux from the soil substrate was solved by residual. So around that same time, we also produced a paper of at the current time there of the types of models that have been developed using land surface temperature, and they range from simple analytical to numerical models. And with this overview article, we also came up with what are some of the challenges in using thermal remote sensing, and those left. For defined there's thermal emissivity issues that are only known approximately. There's atmospheric correction issues. that come about when using satellites. You have to account for that. Remote sensing observations are instantaneous, and in many applications, we need them to be over a longer time scale, like daily. So there's an issue how you integrate that over time. Many of the satellites at the time, especially like GOES, which gave you a lot of observations of land surface temperature, was at a 2 courses scale to look at the field scale. And then the issues of clouds obviously presented another drawback if you're trying to monitor a landscape over time. So how did we deal with some of these issues? Well, already I stressed the point that by using the two-source model, we addressed the aerodynamic issue of radiometric versus aerodynamic. We also utilized a simple formula for adjusting for view angle. And it turns out in most cases, the thermal emissivity is not a big issue for most land surfaces. Still, a study we did fairly early on was to compare uncertainty in some of the key inputs from the two-source energy balance model and a model like Siebel or metric that uses these contextual hot points and cold points. They define, again, like I was mentioning, sensible heat flux at the cold pixel. The sensible heat flux is essentially assumed 0 or slightly negative. At the hot pixel, there's no evaporation. And this defines sort of the land surface temperature, air temperature difference in more of an empirical relationship, however. And what came out of just doing a sensitivity, again, the two-source model is still going to be sensitive to this radiometric temperature uncertainty and also to the fractional cover, whereas models that use these contextual approaches are going to be affected by the selection of those temperature endpoints as well as their relationship to NDVI. So both modeling approaches still have some disadvantages. Now, what came about following this work was the implementation of the idea of using a temperature change over time. This was work that Martha Anderson and George Dyack, who early on was utilizing GOES data to look at moisture variations at continental scales. And the idea was incorporate the two-source energy balance model with GOES information to get you a temperature change and linking that to a simplified mixed layer model, such as the one by McNaughton and Spriggs, so that in combination of the change in temperature with the atmospheric boundary layer model, you could actually estimate the heat flux over that time scale. And from that output, you have the air temperature. So the air temperature and could be derived. The change in temperature is not as is much less sensitive to the actual radiometric temperature. So in other words, we've reduced the effect of having a real accurate land surface temperature using this approach. So in a way, going back to that list of issues, we now have resolved some of the issues with atmospheric correction, because that radiometric temperature change over time is what's needed and not so much the absolute temperature. Following that work that was defined as ALEXI, Atmosphere Land Exchange Inverse Model, came the DysALEXI model. This was then running the regional scale model, producing the output at, say, 4 or 5 kilometers. We then linked into that at the Landsat scale using Landsat or MODIS. At the sub-pixel scale of 30 to 100 meters, we now could have a temperature at that resolution and run the model for these tiles with the air temperature derived from the regional scale model. So now we could run the model and then look at the output and adjust the inputs so that we match at the 5-kilometer scale, the aggregated flux from the 30 or 100-meter scale. So now we had a way of disaggregating the larger scale flux down to the smaller scale. So we've reduced now to some of the remaining issues, which are getting from instantaneous to daily or longer time scales, and how do we go in between the satellite observations. Well, some work that was done by Carmelo Camarelli, along with Martha and myself, we looked at ways of going from the instantaneous to daily, and actually some of the work of Ray Jackson, who was with the Agricultural Research Service back in the early 80s, utilizing the estimates based on solar radiation from instantaneous to daily, that could be a fairly reliable approach at scaling from the instantaneous to daily values. Feng Gao from our group, who had developed a data fusion technique, STAR-FM, originally was developed for spectral measurements. We used it with ET, so we'd estimate ET at the MODIS resolution. We correlate that to the disaggregated Landsat scale, created correlation relationships that then could be integrated over observations of MODIS that continued until the next Landsat overpass. So we could provide a more continuous estimate at the higher resolution based on these correlations between the little coarser to the finer scale. So we sort of addressed these 8 points at some level, and felt like we had a modeling suite that could address the issues that were posed earlier by that Fife article, and have been applying it for water management, drought monitoring, and some food water security. So here are just a few examples of what we've been doing with this type of an approach. So the scaling is really a real advancement, because we could take, geostationary satellites operating at the regional, up from global to regional scale, and use polar orbiting satellites like Landsat, and even connect that to even aircraft or UAV type of information to do the disaggregation. So this is an example over corn and soybean fields in Iowa, where you could see down at this resolution here, if you had this high resolution, you could really see variations in the condition of that surface in terms of crop cover and crop condition. Now, there's still the issue of the latency, because even with Landsat, we have the issue of how often we get these observations. And you can see here there are instances where this particular was a vineyard site as part of our GrapeX project. The gray circles are where we have the Landsat overpass, and the estimated ET from the model is in the black, the interpolated or fused approach, and then the blue is the observations. And you can see we can miss cases where we actually have a drop of evaporation, even though we try to interpolate using actual and potential ET values, that we are missing the mark. And so this is something we're working on actively to try to develop other methods. One of those is incorporating, besides Landsat, other assets of land surface temperature. And so incorporating these include like the EcoStress satellite that was launched, that gives more frequent observations, and the VIR satellite, which is now even better in resolution, that gives us some daily coverage as well. So using this information, using a sharpening technique that can be used to sharpen the coarser resolution down to the finer scale. I don't have time to talk about this technique, but it's showing some utility using these different resolution satellites, as well as the GOES satellite. And so this is being used to help monitor land surface especially agricultural surfaces for water management. One of the things that's being developed is development of these data cube sites over long-term agro-ecosystem research sites throughout the U.S., generating these ET maps over time and then comparing it to ground measurements of ET and surface fluxes. Here's some examples of where we combine Landsat, ecostress, and VIIRS together to estimate the daily ET and comparing that to observations. What you have here is the precipitation and irrigation events. The precipitation is in green, the irrigation blue. You can see in California, there's some heavy irrigation that goes on. And you can see the estimates of ET there in red, and then the observed are both closed and unclosed, which is something I'll talk about briefly near the end, of ET from the eddy covariance towers. And you can see we do a pretty reasonable job in matching what goes on in the landscape. There are some difficulties due to cloudiness that come into play that cause some disparity. But typically we're within about 1 millimeter per day in accuracy with our modeling technique over these landscapes. One important thing to point out, this is better seen here, is here you have ecostress observations that complement the Landsat, and you can see by having these more frequent observations, we're able to pick up some of these deviations in ET that we just don't capture with Landsat in our fusion approach or our interpolation approach. For these two instances, this one down here is alfalfa, so the cuttings, if we don't have an observation during that cutting of alfalfa, when it goes, to a very different ET regime, we're not going to be able to capture it if we don't observe it. But we are finding the utility of this modeling system quite useful in say, monitoring land use changes. This is an example down in North Carolina, a loblolly pine plantation, one clear cut and one that's a mature forest. And what you see here, again, observations in blue. Landsat retrievals are these red triangles, and then the interpolated fuse product there is in red. And there's quite a bit of difference, as you see, between the ET of these two systems. Interestingly enough, the Alexi ET here is virtually the same. So it's a resolution issue that we really need to have. We need to get down to that 30 meters to really capture the land cover, land use changes. The other thing, by using this methodology over time, we're then able to look at cumulative rates of ET for the different land cover types. And so we can start quantifying how land use, and land cover changes will be affecting the cumulative ET over time. So you can see natural forests have a higher ET rate than the two types of loblolly pine forests, and that agriculture is somewhere in between these two. So the other aspect of thermal remote sensing, because it's so tied to the moisture condition of the surface, it's a very good indicator for flash droughts. And flash droughts are conditions where you may still have some adequate soil moisture for the vegetation, but you have an accelerated increase in atmospheric demand over short time frames that can cause stress to the vegetation. And the evaporative stress index, which uses the thermal-based method of Alexi, can capture this earlier than many of the other approaches like the US Drought Monitor, VeggieDry, or some of these other techniques. We're able to capture this change in stress condition that's causing this type of drought condition to occur. And in 2012, it was quite extreme in this region of the U.S. and caused significant impact on yield. The other additional advantage of this approach is that it can then drill down to, again, the field scale to evaluate the impact of drought because of the disaggregation methodology. So this type of technique, I think, is going to be very important as time goes on. There are studies indicating that scenarios of carbon use, even low, medium conditions, that there's going to be more of these flash drought conditions occurring in many of the continents, which is going to affect, obviously, the production of food that we need. So with global observations, then we can utilize this modeling approach over the globe to look at how ET and surface fluxes are changing over time due to climate and anthropogenic effects. The other mention of water and food security, really paramount in arid regions. An example here showing how management practices, in this case expansion of irrigation in this region of Saudi Arabia, is really going to have an impact on the water availability and groundwater. And what we see with this rapid increase in irrigation is things like from the GRACE satellite showing an indication of groundwater trends. But the multi-scaling mapping here, as shown across here, we go from 3 kilometers to 1 kilometer, but it's at the 30 meters where we really see the impact and how irrigated water is being distributed for crop production. So the last part I want to also talk about, well, can this information eventually be used by growers, agricultural ministry, policymakers, because ultimately this type of information becomes very useful to address water management issues. OpenET, many of you may be familiar with, is a consortium of public-private partnerships, number of universities, including USDA, Google Earth Engine, you can see there on the bottom, NASA, Environmental Defense Fund. They're working to develop a platform that will allow this type of ET information to be readily available to growers, researchers, policymakers, to help understand how water is being used and managed at large scale. OpenET uses, besides the modeling approach I talked about today, a number of other modeling approaches that have been used throughout the country, throughout the world, actually, in estimating ET. And part of this effort then has started in the West, where they're producing these ET maps over the Western U.S., where water is a major issue, and making this data available to those who want to use it for various purposes. Part of this work is also going into validation. Here's one of the first papers on this issue, where the models, this is mean total growing season ET, is being compared to flux tower observations collected over these fields. And what's interesting is that the ensemble here, the one here in dark red or maroon, matches the best with flux tower closed. Flux tower unclosed, there's still a bit of a difference. And again, this is an issue that you all are quite aware of, and one that we still need to address. The expansion of OpenET is also going to be over the continental US and beyond. Part of this process is then collecting eddy covariance, flux tower data. There's even some lysimeter data being collected and going to eventually be used to evaluate how these models work over these different landscapes. At the same time, the two source energy balance model is being implemented in Google Earth Engine. It's also being used in Europe by using Sentinel satellites to estimate ET, and they're being compared over various landscapes to assess its utility. One of the interesting studies here that was using a single source and dual source model is that actually when you combine the two together, again, an ensemble, you actually get closer to the observations, or smaller root mean square and bias than each model on its own. So again, the ensemble approach seems like one of the ways that we may improve getting ET values closer to the observations. We still have a number of challenges. One was the latency I mentioned. The other is advection. Advection, especially in irrigated lands, can be significant. Here's an example of the T-Rex project where an almond orchard is next to a large fallow area. It goes fallow. It's a grazing land area that goes fallow in the summer. So you have this major heat source, and the model isn't able to capture some of these large latent heat fluxes that are estimated by the flux tower. But also note that closed and unclosed can have a large variation. So again, the issue of measurements and the impact of advection on measurements is important. One thing to point out, however, with the other real advantage of using satellite remote sensing and its mapping capability is, you can see here the tower is likely seeing the ET largely of the area here, because the winds generally come from this direction, is largely seeing the higher ET rates. But other areas in this field and the adjoining field are quite lower in magnitude. So this kind of capability with remote sensing has major advantages for management and operational applications to determine where there may be problems in the crop condition due to irrigation losses or other factors. So the same issue of advection in the grapex, we also observed this in the grapex study. We had a gradient in conditions over the landscape from Northern California down to the southern extent of California where they grow grapes. The model seems to capture fairly well. Again, there's closed and unclosed values here. Unclosed, open, closed are the solid circles. And you can see that we capture reasonably well the fluxes. We have more challenges down to where we have, again, stronger advection, hotter and drier conditions, more irrigation occurring. And so this is an area that needs further study. This study here that was in irrigation science by Nico Baumbach compared various ways of energy balance closure. This is on an annual basis. And what you can see here, as I've marked off, the two kind of greenish ones are the observed ET, either daytime or total. And then these other in different colors are different closure techniques. And as you can see, especially as you get more and more advective cases, you can get some significant variation in what the estimated ET is, or quote measured ET is for that landscape. So this is a challenge in irrigated lands in particular that needs to be addressed. So this is my little advertisement for what's coming up, a Chapman conference being held in Boulder, Colorado in 2025. And as you can tell from the title, we really want to try to address this energy balance closure problem. And tentatively, the topics include both the theory and instrumentation and measurements, the environmental challenges, because different landscapes are going to have different issues in trying to measure fluxes and then addressing energy balance closure. There are also other techniques besides eddy covariance that might provide us insight into some of these issues. there's broader implications, as I've mentioned, about, making water management decisions, policy issues. And it just doesn't involve water, but carbon and other trace gas fluxes. And so we hope to address some of these and come up with some recommendation and best practices, and what could be future research directions that need to be considered as we try to address this problem. So what I want to leave you with is what satellite ET and energy balance estimation can be done using land surface temperature. We believe it can improve accounting for current water use and crop productivity. It can monitor changes in water use with changing climate, land use, and population. It can be used to improve hydrologic monitoring, as well as the use of what I mentioned earlier, water balance models. It can be used in conjunction with water balance models to help to refine these models in unique cases. And it can help with crop stress detection and yield estimation, in particular with flash drought. So I think I ended on time. I appreciate the time you spent with me today to learn about land surface temperature and its use on evapotranspiration and surface energy balance models. So thank you, and I'll take any questions.
Thank you, Dr. Bill Kustas, for sharing your insights on thermal remote sensing, its application. So, yeah, we can take Q&A. And do discussions. Yeah, you can raise your hands or just turn on your audio and just ask away to Dr. Bill Kustas. So I have one question to you. So you mostly talked about the thermal remote sensing techniques based on satellites, and now there are more thermal techniques that can be used at the field level. So with the advance of techniques, more people are employing like thermal camera that can be installed at the site level. And do you have some of the insight you can share with those, the community, proximal remote sensing community who use thermal remote sensing techniques, and what we need to do to advance this evapotranspiration side?
Yeah, I think some of it, some of these tower-based techniques using drones, they're very useful from a research standpoint because they can provide even higher resolution information about surface temperature and how it may relate to the conditions on the surface, whether it's surface energy balance or ET. It's also useful in interpreting what might be observed at the coarser resolutions we get from satellites. We're seeing that with drone work that's being done as part of T-REX and GRAPE-X, where they're measuring, they can actually separate the canopy and soil substrate elements, surfaces, and can derive component temperatures. And those can be used to compare to, the models we're running at 30 meters or 100 meter scale resolution, where we try to do that partitioning. And that'll give us some better insights as to how our formulations may or may not be as accurate as they could be, depending on developing new techniques to improve those. There's some interesting work going on trying to use this model in phenotyping approaches, where they want to have very small scale plots where they're looking at different genotypes and trying to understand how water use, and yield relate to the different genotypes that they're growing. So there's potentials outside of that.
Thank you. I do see some questions in the chat. So Paul asked you, have you experimented with planet satellite data?
I have not, although we have an ongoing or soon to be ongoing research project with Planet to see the types of information they can provide at the resolution of Planet for biomass and leaf area and plant condition could be integrated into the modeling schemes we've been working with. The nice thing about our modeling scheme is that it can disaggregate, like I had mentioned, down to the UVA level. And that's really will be interesting to try to do that where we try to incorporate other types of satellite information.
And Josh asked, what are your thoughts on future directions, what's needed, and what do you see on the horizon that's exciting to you?
That's a big question, Josh. Well, certainly, I think, the potential, I think thermal is being recognized as a real potential, and that potential needs to incorporate more observations, more satellites. Josh is with Hydrosat, and Hydrosat is going to deploy a bunch of small satellites to provide daily, perhaps daily thermal at high resolution. And that type of information can be really valuable, as I had pointed out, when you have these significant changes, dynamics in ET caused by management conditions or atmospheric demand conditions. And so more observations gives us better information about what's happening at the surface. So I think that's one thing. And the second thing is some of the work we've been doing, Wade Crow from our group has been incorporating data assimilation and his water balance modeling with ET estimates based on the TSED model and other techniques. So trying to merge prognostic and diagnostic modeling approaches and leveraging the strengths of both, I think are another interesting and approach to go with. I also, I'm seeing more and more deep learning, machine learning approaches using land surface temperature and ET observations and trying to incorporate that as a vehicle. I mean, I think there's value in that. I think just going with one over the other is probably not advisable. I really think that physical models still need to be incorporated in any approach that we use because of their ability to capture variations that just aren't going to be in the observational data per se.
Okay, and Tilda Myers has raised hand. So can you speak up?
Yeah. Hey, Bill, nice presentation.
Thank you, Tilden.
For first question is, so do you make any adjustments when you're dealing with trying to come up with flux estimates and like complex terrain? And number two, would information from, let's say, boundary layer thermodynamics be useful in terms of providing additional information to run a two-source model?
Yeah, so the first question about complex terrain is one that, I think a big aspect there has to be how do we factor in the radiation effects or the effects of topography on radiation loading and how that's going to impact the fluxes. And there are a few techniques in trying to do that. We, working mainly in agricultural lands, we haven't haven't had as much of an issue there, but we certainly, if we want to do something at the continental scale, we're going to have to factor that in. So so that's something that Martha Anderson in our group has been working with Chris Hayne at NASA and trying to incorporate that. I think the other thing is snow. I mean, snow is such a difficult surface to model any type of technique. We actually did the two source energy balance model and got interesting results, but we haven't seen how that would work. As far as the second question about incorporating some boundary layer dynamics, I think that's one of the ways we go. We're looking at landscapes with strong advection, for example, work on the vertical flux. The horizontal flux we really don't capture in our modeling approach, and there hopefully might be ways that we can capture that and not require running a large eddy simulation to do that. But I think we need to do those kinds of experiments where we use large eddy simulation and observations of the boundary layer to see, you know, how well we can capture that with some simple parameterizations or adjustments in our approach.
Thanks.
Okay.
Until
So we
you're going
have
to be at our meeting, right? At the Chapman conference.
Yes.
Okay, great.
Okay, so we have two more questions in the chat. So Dennis asks you, what are your views on coupling water and carbon fluxes to assess evapotranspiration better over diverse landscape management and drought conditions?
Yeah, so the carbon side hasn't been a focus, but I think if we incorporate a strategy, for example, with a transpiration component using, for example, a light use efficiency approach for the transpiration, or perhaps even another type of approach that incorporates the effect of carbon, be very interesting to try to see how that information together with the thermal response can help us understand that carbon water coupling better.
Okay, and there is a question, could the integration of soil moisture estimates from remote sensing, such as SAR, be useful to improve estimates, or are these too coarse to be useful?
I'm sorry, that you were kind of broken up there. I didn't cap.
Is that yeah, sorry.
There's one. Is there one by
Yeah,
soil moisture estimates?
Yeah, so integration of soil moisture estimate from remote sensing be useful to improve estimates, or
Yeah,
like
so
yes, SAR, for example,
SAR.
or are they too coarse to be useful for estimate soil moisture and moisture transpiration?
Yeah, so no, I think there's real value if we can couple soil moisture estimates along with the thermal. Wade Crow from our group has been doing that, trying to incorporate SAR from Sentinel. Was it Sentinel? Is it Sentinel-1? Incorporating surface moisture derived from there in the modeling approach. The other value is with soil moisture estimates for microwave, even if they're surface moisture estimates, they're really tied to the soil evaporation. So it could be another way of sort of bootstrapping the methodology. If you have an independent soil moisture based evaporation component that you're deriving from microwave, that could that could help to constrain the models using thermal, because now you have an additional estimate that could help to sort of contain the output from the model, or improve it. So yeah, I see value there.
Okay, great. Now it's 10 o'clock, so I think I have to let Dr. Bill Kustas go. But thank you, Dr. Bill Kustas, for sharing your precious insights. And today's presentation is recorded and will be uploaded to the AmeriFlux YouTube channel in the coming days. And the next speaker in this series is Dr. John Gammon, which will be on June 14th. So stay tuned for that. And thank you for joining us, and see you next time.